In the last term, we have started the topic of map. Okay. So in the map, we have learned about three concepts. Basically, it was, I think, so two concepts in the last term. So when we were discussing about the map, there were first about the classification of map, and there were two basic classification was given to you. So on the basis of the content that is present on the map, there can be a topographic map or it can be a thematic map. So topographic map is basically a general purpose map that contains all sort of information. Okay, they are not particular to a certain theme, but they are a general purpose map, and usually the national mapping agency of a country produces that map. Like in India, we have Survey of India. In United States, there is USGS. So through that, these type of topographic maps are obtained, and we are also working on the topographic maps in the laboratory session. The one of the very important use of the topographic map is determination of administrative boundary. Okay. So we will know about the administrative boundary with the help of these topographic maps. Second thing was thematic map. Okay. So thematic maps are those maps which are based on a particular theme. They are created for a particular theme, like road map, water map, soil map, temperature map, something like that. So they are based on a particular theme. Then we have started these issues in the mapping. First one about the purpose. And the purpose says that whatever content we are putting on the map, because basically we are creating a picture of the real world. We are trying to portray the real world on a paper map. So when we are doing such type of portrayal from real world paper, it is not possible to include each and everything whatever is present on the ground in the map. Otherwise, it will be impossible to create a map. Like when we take the example of image, I have shown you the image, and it says that when we talk about the image of an area, as you can see on the screen. So when we open the image of an area, it will be a snapshot. Whatever is present on the ground, it will be given on the image, because image is a snapshot of reality. But when we talk about the map, you can see this is 1:50,000 scale map, and at this scale, several things are missing. Why? Because we cannot include everything. So what we are going to include and what we are going to reject, it depends upon the purpose of the map. So with the help of the purpose, like suppose if we are creating some map for the education purpose. For the school students, we want to show them all the continents or all the countries of the world. Okay. So whatever map we are creating, we will try to make sure that all the labeling of continents and the countries should appear properly. It depends upon whatever is the purpose. In that case, the river, the contours and other things will not be given over there, because our purpose is education, academic purpose, so that a child will know the name of the continent, the child will get to know about the name of the countries around the world. So it depends upon the purpose on the basis of which the content of the map is included. Then second thing is scale. So what is the scale? Again, when we are taking a map, we cannot portray everything as it is. In that case, what we need to do, we need to make a certain scale, certain ratio at which the real world get mapped on the paper. For that, we need to define a scale. So scale can be defined as the ratio of a distance on the map to the corresponding distance on the ground. In the last term, you have seen the comparison between the large scale map and the small scale map. Just open your notebook and see the differences that we have written down. Small scale map and large scale map. the scale can be represented in three different ways: in a ratio form, in a verbal, and in a graphical form. Okay. So the ratio scale is like a ratio, or it can be like a division, like 1 is to 50,000, 1 is to 10 lakh, and so on. Second way of representing the ratio, just wait for a minute. So when we take a scale in a verbal form, it will be represented like 1 centimeter represents 50 meter, or 1 centimeter represents 10 kilometer. The third way of representation is a graphical scale or a bar scale. In this, as you can see, that there will be a bar that will give you certain numbers like this: 0, 100 kilometer, 200 kilometer. And later on, you can take the measurement from the map to this graphical scale. So in the last time, it was described in detail how to interpret this graphical scale. We have seen the difference between and the comparison between the large scale and the small scale map. So as you have seen that if we compare these two maps, one is to 5,000 and one is to 10 lakh, which one is a large scale map? 1 is to 5,000. Okay, and which one is a small scale map? It is 1 is to 10 lakh. Then in which the level of detail is more? 1 is to 5,000 will give you more detail as compared to 1 is to 10 lakh. If we see that area covered, 1 is to 5,000 will cover lesser area as compared to 1 is to 10 lakh. Okay. So this was the comparison that we have seen. And another thing was regarding the image. Then when we talk about the image, there is a spatial resolution. And when we talk about the map, in that case, we will have a scale. With the help of this scale, you can convert any distance on the map to the equivalent distance on the ground. Okay. So if somebody asks, if you measure 1 centimeter on this map at the scale of 1 is to 5,000, how much distance will be on the ground? So answer will be 50 meter. It is not just only the, we can also compute the area according to it. After that, we have seen about the spatial entities. There are three basic entities in GIS: point, line, and polygon. Okay. It depends upon the scale that helps us to decide which type of spatial entity will be used to represent any of the object. Like at 1 is to 10 lakh scale, something will be represented by a point, but the same thing will be represented by a polygon at 1 is to 50,000 scale or 5,000 scale. There are three entities: point. The point says anything that have a location, then it will be a point. Okay. Okay, so when we have a location, in that case, we will represent it by a point in the form of latitude and longitude or XY coordinate. Okay. Then when we go for a line, what is line? Line is an ordered pair of coordinates. Okay. So if there is a particular order in which line will be created. So anything that have a length but do not have a width, in that case, we will go for a line. Then what is area? Anything that is going to cover an area, it will be represented by the area or a polygon. And the definition is similar to the line. It says An ordered pair of coordinate where first and the last point are the same. So broadly, there are three types of spatial entities: point, line, and polygon. An extension of them is, for line, it will be network, and for the area, it will be the surface. Yes, any question? Okay. So for the spatial entities, you have seen like the NYC subway station example was given, the school location example was given. So everything was like a point in the map in the given area. Then you have seen the example of roads, streets. They will be represented by a line by an ordered pair. After that, you have seen the example of villages. So villages were represented by a polygon. Okay. So this is how the point, line, and polygon are represented over there. In today's term, we are going to start with the generalization. Okay. So what is generalization? As we have just discussed, that whenever we have to represent anything on the map, basically we have to remove some of the details, okay, so that the map become readable. For that purpose, we need to perform the generalization. There are several techniques through which we can do the generalization. First, I'm reading this thing and then I will explain it with the help of example. And later on, we will see the different methods through which the generalization can be performed. So in cartography, generalization means either the process of producing a graphic representation of smaller scale from a large scale original, or the process of deriving a coarser resolution from a more detailed representation within a database. All spatial data are a generalization or simplification of real-world features. In some instances, generalization is needed because data are required at a particular scale. In other cases, generalization is introduced by the limitation of the technical procedures used to produce data. A geographic database cannot contain a perfect description. Instead, its content must be carefully selected to fit within the limited capacity of computer storage devices. Therefore, it needs generalization. It is necessary to understand the objective why we generalize, an assessment of the situation which indicate when to generalize, and an understanding of how to generalize using spatial and attribute transformations. Okay. So there is a digital generalization, like first thing says, why do we need to generalize? Second thing is situation assessment, that is when we need to generalize. And final part is how we do the generalization. Now, coming to the first one, when to generalize, when there is a need to generalize. It is listed over here that whenever we have a difficulty in reading, okay, if the map becomes too busy or it is full of detail, in that case also you cannot read it. So first of the reason is that if the map is not readable, in that case we need to generalize so that it will become more readable, more clear. Okay? Like if you draw something on a paper and if you try to put all the detail over there, okay, in that case what will happen? Nobody can read that thing. Similarly, in case of map, if the cartographer tried to put everything on the map, then it is not possible. Okay, I have shown you the image and said that it is a snapshot of reality. But when we go for a map, basically what we need to do, we need to pick some of the things on the real world and then perform the mapping of those things. Okay, so this is what the generalization is, that when there is a difficulty to understand anything, we need to do the generalization. Similarly, we are scaling down the reality. So whenever we are doing this scaling down, it is possible that things become, the distance between the things will not be possible to show and they start touching each other. So in that case also we need to do the generalization. Okay. So I'm just reading it out. The situation in which generalization would be required arise due to the success or failure of the map product to meet its stated goals. This is during the cartographic abstraction process. The map fails to maintain clarity with appropriate content at a given scale for a map purpose and intended audience. Following conditions may be used to determine a need of generalization. First is congestion. It refers to the problem when too many features have been positioned in a limited geographic space. That is, feature density is too high. Collisions refers to the condition when the features will touch each other. For example, the separating distance is smaller than the resolution of the output device. Imperceptibility. A situation results when features fall below a minimum portrayal size of the map. At this point, the feature must either be deleted, enlarged, or exaggerated. So these are the conditions when we need to perform the generalization. Okay. This very figure is showing the this concept of generalization. Okay, as you can see on the screen, all the maps are of Mississippi River. Okay, these all maps are of Mississippi River, and when you straight. So the first map is at 1:20 million scale. This one is the map of United States of America. Now you can see the Mississippi River. And this Mississippi River is shown just by a single line. Okay, it's like a thread how the Mississippi River is flowing. So it will give you a basic idea about the location of Mississippi River, possibly the states through which this Mississippi River is flowing. Okay. But try to observe that difference in the portrayal of the same Mississippi River at different scale. Okay. Just try to understand what is given over here. First figure is at 1:20 million. Second one is at 1:50 million. Third one is at 1:250,000. And fourth one is 1:50,000. There is the same area, same Mississippi River, but the portrayal is different in every diagram. So the first 1:20 million, Mississippi is just by a line. Okay, but at 1:5 million, you can see that tributaries of the Mississippi River, Red, Arkansas, Ohio, all these are the tributaries of the Mississippi River. This information is not available as 1:20 million because it is not possible. Like, try to think that if all these information is given at 1:20 million map, probably it will be shown just by a small dot. That's it. So it is not possible to read that thing at 1:20 million. But at 1:5 million, it is giving you the basic information about the tributaries of the Mississippi River. Now come at 1:250,000 scale. You know, the meandering of the river. Okay, this is called the meandering. Okay, this type of curve. This is the meandering of the river, and at 1:250,000 scale, the meandering of the river is given. Okay, the width of the river is also given. In the previous 1:5 scale, the river is shown by a line. But now you can see at 1:250,000 scale, the same river is shown by a polygon, not by a line. Coming to 1:50,000 scale, now at this scale, the depth of the river is given 20 million, 30 million, the bank, the shore, the sandy region of the river, everything is given at 1:50,000. So now you can understand what is generalization and how the depiction of the same river is getting changed when we are using the different scale. Okay. So generalization will be very, very high at a small scale map, And as we go towards the large scale map, the generalization will be lesser. Okay? More and more detail will get depicted on the map. Next one is, you have learned why do we generalize and when do we need to generalize. Now we are coming about how to generalize. There are so many different methods through which we can perform the generalization. Open your notebook and write down the methods, because the methods, there will be 8 to 10 methods over here and the name will be similar. So don't get confused among the different form of generalization. Listen this thing carefully and note it down in your copy. Okay. First thing is simplification. Before coming to the concept of simplification, first see the diagram of simplification. As you can see over here, what is the change has taken place? You know, how many points are there in the black color line, thick line? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Now see the second one. 1, 2, 3, 4, 5, 6, 7. First one is the original map. Second one is the generalized map. Okay. You can see the difference between the original and the generalized map. The number of samples, number of points that are used to do the digitization of the feature is reduced. Okay. This is what the simplification is. In simplification, we try to reduce the number of points through which the digitization has taken place. Okay. First, I am reading it and then I will show you the example, another example on the ArcGIS software. Yes.
Ma'am, there is word written over here at 50% scale. If we are saying that scale is 1:5 million, then at 50% scale means 1:250,000. That 2.5 million, is that mean?
It may be for that one, but the basic thing is it is not showing you the exactly scale. Okay, they are just doing this thing for the representation purpose so that you can understand what it is happening. Like when we were saying that something is at a large scale, means what you are saying that 1 is to say 50,000 will become 1 is to 25,000 at 50% scale. Means we cannot comment on that one, but yes, it is going to reduce. Okay. Like if the first one is at 1 is to 50,000, the second one might be at 1 is to 25,000, or it might be at 1 is to 20,000.
Okay.
So a digitized representation of a map feature should be accurate in its representation of the feature, that is shape, location, and character, yet also efficient in terms of retaining the least number of data points necessary to represent the character. Okay. So this thing is important, that representation of the feature will remain same. As you can see in the diagram, okay, the previous means original map and the generalized map, the line is going in the same direction. The shape is more or less same. Okay, but you can see a slight curve that is coming at the between second and third point is missing now. The second and third point are removed and first and fourth are directly get connected. So the small subtle changes that are taking place in the original map, these are removed in the generalized. So when there is a reduction in the scale, okay, when something is going at a smaller scale, that information you can see is coming more properly when we are going at a reduced scale. Then simplification operators select the characteristic or shape describing points to retain and reject the redundant point, considering to be unnecessary to display the line character. What is the advantage of simplification? It will reduce the plotting time. It will reduce the storage, less problem in attaining plotter resolution due to scale change, quick vector to raster conversion. So let's see this example simplification. Okay, right now on the screen I have opened one of the line feature that is digitized over here. Okay, if I double click on this one and check the number of points that are used to digitize this particular line, it is 457. Okay, you can see it over here. There are 457 number of points that are used to digitize this simple line. Okay, this much number of points is not necessary. Okay, like suppose if I do the digitization, okay, if I do the digitization of the same thing, now you can see the same line I have digitized it over here. Okay, now you can see the number of points for this one. So I've used just 35 points over here. Okay, I have used just 35 points over here, and previously it was 457 points. Okay, although the shape is not that much good as the previous one, but still the number of points have been reduced significantly. This is what happens when we do the simplification. We try to retain the original shape, but we remove or we reduce the number of points that are used to digitize that feature. We have already done the digitization in the laboratory session, and in that one, as it is suggested to you that whenever you are doing a digitization, try to take lesser number of points when the feature is straight. Okay, and if there is any curve, then take larger number of point at that place, because every time the point is get connected to the next consecutive points by a straight line. So this is how we do the simplification. We reduce the number of points that are used to create that object, and if we reduce the number of sample point, it means lesser number of points are used, less amount of storage will be required. If you open that object, it will take less time to display and other things. So this is what the display basically involves reduction in the number of points. Write down the second one, smoothing, and try to figure out how the smoothing is different from the simplification. As you can see over here, the original map has the number of points 1, 2, 3, 4, 5, 6, 7. Okay, and the generalized map has 1, 2, 3, 4, 5, 6, 7. So the number of point remains same, 7 in both the cases. And when we do the generalization, when we do the smoothing operation, The sharp curves that are present on the line, those curves has been removed. They have been smoothed. So this is what the smoothing operation is. The number of sample points will remain the same. In case of simplification, the shape was remain same, but the number of sample points were reduced. But in case of smoothing, what will happen? The sharp curves are removed. So it is the replacement of sharp and complex forms by smoother ones. These operators act on a line by relocating or shifting coordinate pairs in an attempt to plane away small sharpness and capture only the most significant trends of the line. A result of the application of this process is to reduce the sharp angularity in the feature. Again, I will show you the same thing on the ArcGIS. Okay, like suppose, going to the instead of taking the different image on different digitized tool, I will show you on the existing one. Like on the screen, you can see the lower one. I'm just deleting the upper one. Okay. On this particular feature, you can see that there is a small, this is a curve over here. Okay. So there is a smoothing required over here. So what will I do when I will perform the smoothing operation? I will displace the vertex to a new position. So the previous curve will be removed. Are you getting it? This is what happens in the smoothing. The number of points will remain same. Okay, again here you can see a small sharpness over here. That is, I will change the position. This is what this smoothing is. The number of sample points remains same, but the sharp curves are removed over here. This is what happens when we use the smoothing operation. Next one is the aggregation. Okay. What is aggregation? Write down this term first, aggregation. See the figure, then I will tell you what is aggregation. This is the third one. First one was simplification, second one smoothing. Now this one is the third, aggregation. Write down the term aggregation and see the figure. So as you can observe in the figure, there are some ruins, okay, and those ruins are replaced. They were previously shown by a point, but after the generalization, they are coming like a polygon. Okay. So this is what the aggregation is. When we have point features, okay, like there will be some ruins and there will be different buildings of the ruins. So instead of showing by points, all the points are aggregated together to the polygon. This is what the aggregation is, because when you change the scale, these points will become invisible, they will get lost. So in order to preserve these ruins, what will take place? This type of aggregation will take place so that this point will get converted into the polygon. Okay, so aggregation, there are many instances when the number of like point features within a region prohibits each from being. The point features must be aggregated into higher order class feature areas and symbolized as such. It is the replacement of large number of distinct symbolized objects by a smaller number of new symbols. In simple words, it is basically a replacement of large number of points by a smaller number of polygons. Okay. For example, if the intervening space between the houses are smaller than the physical extent of the building themselves, the buildings can be aggregated and re-symbolized as a built-up areas. Okay, so instead of showing building, hut, and other things separately, they will aggregate it together and will be shown as a built-up area or settlement area. This is what the aggregation is. Okay, write down in your copy. Point and it will goes to the polygon.
Ma'am, can repeat your aggregation?
Sorry.
मैम फिर से एग्रीगेशन रिपीट कर दीजिए.
Achha. So when we do the aggregation, basically we are going to replace the point. Okay, we are going to replace point by the polygon. Okay. This, the point will get converted into a polygon. Okay, this is what will happen in the case of aggregation. Why this type of conversion is taking place? Because, like, suppose, try to think, you have a map at 1:5,000 scale. Now in that case, the building and the building, multi-story building, the individual unit of houses, the hut, everything will be represented separately. But when you change the scale from 1:5,000 to 1:50,000 or 1:1 million, in that case, you cannot show that thing. Okay. So what will happen? All these things will aggregate it together, and instead of showing these things individually, they will shown by a polygon, and that polygon will be labeled like built up area. Okay. Instead of building, hut, and other things, there will be a built up area. So this is what the aggregation is. In order to preserve the feature, when there is a change in scale, the point is converted into a polygon. Okay. I will try to show you the example of this one. Just wait a minute. Like as over here. Okay. This map is on the screen. I think so it will be visible. There are two squares over here. This map is at 1:50,000 scale. And when this map is changes to 2,50,000 scale, the same thing is represented by a polygon. You can see there are small points over here like this 1 point, 2 points, and small other things over here, built up things. Okay. But when I am changing the scale 1:50,000, the same thing is represented just by one polygon. Yes. No. So this is what the aggregation was. Now I'm moving to the next one. Write down amalgamation. Amalgamation. And what will happen in amalgamation? In case of amalgamation, polygons will get converted into a polygon. Means large number of polygons will get converted into a single polygon. Okay. So just try to see the same thing on the map on this figure. Okay, so In case of amalgamation, it is a replacement of several area objects by a single area object. Though amalgamation of individual features into a larger element, it is often possible to retain the general characteristics of a region despite the scale reduction. For example, an area containing numerous small lakes, each too small to be depicted separately, that could be judicious, that could be depicted separately, could with a judicious combination of the areas retain the original map characteristics. Okay, so basically what they are saying that in this case there are large number of polygons, and when you are doing the generalization, in case of amalgamation, the large number of polygon will get converted into a single polygon. Okay, so I hope so this difference between the aggregation and amalgamation will be clear to all. In case of aggregation, points are getting converted into a polygon. They get aggregated into a polygon. In case of amalgamation, the spatial entity will remain same. Before the generalization and after the somebody is not on mute. Please mute yourself. There is a lot of traffic. It's okay now. Yes. So this was the amalgamation, where a large number of polygons are replaced by a single polygon. Next one is the merging operation. Okay, what is merging? First write down the merging and then see the figure. So basically it is the replacement of several line object by a smaller number of line object. Like in the original map, there are 1, 2, 3, 4 lines. Okay, these 4 lines are now shown by just 2 lines. The 2 lines between the 2 major lines are get merged with the main stream. This is the merging operation. In case of merging, the line object, okay, the object will remain same. It is the replacement of several objects by a smaller number of line objects. For example, divided highways are normally represented by 2 or more adjacent lines with a separate distance between them. Upon scale reduction, these lines require that they be merged into one positioned approximately half between the original two and representative of both. Okay. So this is what the merging is, and merging will take place of the line objects. Next one is collapse. Write down collapse and see the figure again. So what is collapse? As you can see from the figure, it is the replacement of polygon. Okay, this one is, if you see the lake in the original image, and this area of the lake is represented by, this region of the lake is represented by the area. But if you see the generalized map, this lake is represented by the line at this part, and later on it is by a polygon. So it is the replacement of an area object by a combination of line and area, point and line objects. As the scale is reduced, many area feature must eventually be symbolized as points or lines. The decomposition of line and area features to point features or area features to line feature is common generalization process. Okay, so what will happen in this one? In case of collapse, polygon will be replaced by line. This is for the collapse. Okay, that the polygon will be replaced by the line or by the points. Next one is refinement. Okay. Refinement is the replacement of a complex pattern of objects by a selection that preserves the pattern's general form. Okay. So this is how the refinement took place. Write down it in your copy, refinement, and see the figure. The figure for the original map, the pattern is quite complex in that case, but you can see the generalized map. Okay, the generalized map, the pattern is preserved in case of generalized map. Okay, so this is what the refinement is. The complex pattern is replaced by the simpler pattern. Next one is the exaggeration. Write down the exaggeration and see the figure. So you can see the difference in the exaggeration before and after of the map. See the bay and inlet area. So if there is a change in scale, if there is a reduction in the scale, the small gap between bay and inlet, there is a very narrow gap between them. Okay, so if there is a change in scale, this narrow gap will not appear. Okay, so how the water will go inside? So that's why there is a need to exaggerate this portion so that it will be clear that water is going from this place. So that's why in order to preserve such type of gap, narrow gaps, we need to exaggerate the things. Okay, so it is the relative enlargement of an object to preserve its characteristics when these would be lost if the object were shown to scale. For example, inlet need to be opened and stream need to be widened if the map must depict important navigational information for shipping. The exaggeration may lead to feature conflict and therefore require displacement. After exaggeration, the next thing is displacement. Okay, write down displacement, see the figure. The displacement is very obvious. Okay? You can think like there is a road line going parallelly to the railway line. You may have seen that the road and railway line both are parallel to each other at many places. But in the map, you have seen that there is a gap between road and railway line. So such type of displacement is necessary so that both the feature will appear properly to you. So that's why there is a displacement between them. It is the moving of object from their two true positions to preserve their visibility and distinctness. Feature displacement techniques are used to solve the problems that arise when two or more features are in conflict. Okay? So you can see the difference in both before and after the displacement of the road and railway line. So this is about the different types of exaggeration. Now I am giving you 10 minutes break, and after that I will show you some of the example of exaggeration on the Prayagraj map. You already seen the 63G map, the old surveyed map. After the break, we will see these displacement over there. Okay, so 10 minutes break and then we will start the class.
Ma'am?
Yes.
Ma'am, have you uploaded this PPT?
I'm not sure. I don't think so. I have uploaded it. Let me check. Is it appearing on your MS Teams or not?
No, ma'am, it's not.
Then I will not upload it. Just let me check. No, it is not there. I will upload this one today.
Ma'am, one more thing.
Yes.
Thank you.
Ma'am, in the calendar section, I don't think so that हमारा time जो classes का time schedule है that is appearing.
I think so. It is appearing for all the students.
Maybe actually I have checked yesterday, so that's why I have mailed you yesterday last night.
Anybody,
Maybe
rest
is
of
it
the
that I
students,
am
please
not able to
confirm.
do it, or the rest of the classmates are able to see it?
Ma'am, in my one it is showing.
Because my all the calendars, there's all out blanks, nothing is being appearing.
Okay, I will do one thing because it was Praveen.
Yes, ma'am.
Are you facing the same problem?
Yes, ma'am.
Yes. Okay. So I will do one thing, although I do not know, Praveen, why that thing was happening with you, because you was already there in the team. I have checked later. Your name was there in the team. I will do one thing. I will cancel the meetings and I will schedule the meeting again. Maybe after that it will appear on your calendar.
Okay, ma'am, sure.
But otherwise,
Okay,
the
ma'am.
class, Vibham, how have you joined this class? Because if that thing was not appearing in your calendar, how did you
Ma'am,
join it?
we had get the access of Microsoft Team with the ID and password. So it
Yes.
was asked to change the passwords and all those things. So I have done all of that.
Hmm.
But yesterday, I think that day before yesterday, Varun sir had emailed you regarding my joining.
Yes. Yes.
So I have just, ma'am, you have added me in the group and I was able to see all the lectures and PDF. But when I checked the calendar section, so there was no schedule of the classes, ma'am.
No, how
So
did you
that,
join this class? If the calendar, if it was not appearing in the
yes, yes,
calendar,
ma'am,
how did you join?
I had emailed you yesterday. So you told me the timing, and I opened my Microsoft Teams. So there was a link to join the meeting. So I
Yes.
just clicked on the joining, and I was in the class.
Yeah, that's it. Yeah, this thing happens.
Yeah.
No, if that thing is appearing coming, then there is no problem. Sometimes this happens that even with us also that the schedule does not appear on the calendar. But
Mhm.
when we go to the team, the things were coming at that place.
Okay, ma'am. So this was my question, because maybe if the classes are changed or the timings are
No,
means.
that thing will appear on your MS Teams. Okay.
Okay.
And
Okay.
usually there will be no change in the timing. There is an exception on 29th because there is
Yes,
an
yes,
exam at
yes,
that
ma'am.
day. But otherwise, there is no disruption in the schedule or other thing.
Okay, ma'am. No problem. Thank
Praveen,
you.
welcome.
Yes, ma'am.
Praveen, you also check your MS Teams, GIS technology teams, whether the meeting is coming in that one or not, because it should be appearing at that place inside the GIS technology team.
Okay, ma'am.
आप GIS टेक्नोलॉजी टीम पर जब क्लिक करोगे वहां जाओगे तो वहां पर आपका मीटिंग आना चाहिए। ये तो मतलब कैलेंडर में नहीं आना, ये कोई बड़ी वो नहीं प्रॉब्लम है, क्योंकि ये हम लोग के साथ भी होता है कि कुछ ऐसी मीटिंग्स होती हैं जिसमें कैलेंडर में नहीं दिखता, लेकिन टीम पे जाते हैं तो वहां पर वो आता है। अगर आपकी टीम्स में भी नहीं आ रहा है तब मुझे बताइए।
मैम मैंने कल इनको सेंड किया प्रवीण जी को टाइम टेबल, तो शायद अब इशू ना हो, ऐसा मैंने इनको कर दिया है।
ओके प्रवीण, आप चेक करके देखिए MS टीम्स पे आपके आ रहा है कि नहीं। GIS टेक्नोलॉजी टीम को चेक करिए।
Okay, ma'am. Yes, ma'am. GIS technology show कर रहा है Teams में।
Okay, let's start the class again. Before going to the break, we were discussing about the generalization, and you have learned about different generalization techniques. Right now on the screen, you can see a large scale map. Okay, there is a river Ganga, and you can see small streams that are coming out from the river or this sand region. Is it visible to everyone?
मैम
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
You can see over here that these are represented by a polygon, isn't it? And now let's see how the same thing is represented at 1:250,000 map. So I'm just unchecking this map, and the map which is just below the 63G15 map. Yes, now you can see that instead of showing them by a polygon, a straight line is used. That is, now the polygon is replaced by a line. And second thing, this is one, and second thing is the reduction is number of line. This number of line, there are just 2 lines over here. Okay, but if I open the large scale map, there are 1, 2, 3, 4 different small polygons. Yes, 4 small polygons over here. Okay, so this is what is the name of this generalization, where polygon is replaced by a line.
Collapse.
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 Yes, collapse. So in the collapse, we have seen in the theory session that polygon is replaced by point or lines. So you have just seen this example of this one, that the polygons are replaced by the line over here. Okay. Just wait, I will show you another example. Now I'm just going to open another. There's a little bit screen lag, I think so. Just wait. Yes. Now you can see there is Sanwa Kalon overhead tank. Okay. See this overhead tank, and there are so many small rectangles that are drawn over here. Okay. Have you seen? So this one is a large scale map. Okay. Now observe the change when we are going to a smaller scale map. Okay. Just see the boxes, the rectangles that are used to draw at a large scale map. You can see 2 overhead tanks over here. Now, when we move to the next level, see the change. You can see all those overhead tanks are now replaced by point. Okay. So what is this? Replacement of point, polygon by a point. Again, same. Collapse. Yes. Now this one is a small scale map. Okay. You can see the black line over here and the red line over here. The black line is the railway line and the black line is the road. Okay. Now what I am going to do, I'm going to change the scale now because there is a little bit screen lag. It will take time. So you should see the difference. Is it visible? The difference is visible to all. The gap between the road and the railway line. This one is a large scale map. So previously it was small scale map. And you can see that there is a change in the distance between railway line and the road. So What is the name of this generalization?
Displacement. Displacement.
Displacement.
Displacement, ma'am.
This one is the displacement. Just wait. Yes. Right now on the screen, you can see from the river Yamuna, there is another river. Sasur Khaderi Nadi is going from this river Yamuna. Is it visible to everyone? This black color line.
Yes, ma'am.
Okay.
Yes,
Yes,
ma'am.
ma'am.
Now see the
Yes,
shape of this line, see the curves, the meandering of this particular river, the Sasur Khaderi Nadi. See the meandering of this river, how it is appearing at a large scale map. Now I'm changing the scale of the map. That same river is now shown by this light green color over here. Okay. And see the change in the shape of the river. Okay. So what is happening? Basically, smoothing is taking place. The sharp curves, some of the sharp curves are removed so that the river remain preserved when there is a change of scale. So this is going, there is a lot of things that are coming over here. If you open one by one, you will find so many generalization, because without generalization, it will not be possible to map the area. When we are changing the scale from, there is a significant change in the scale. This map is 1:250,000, and the another map is at the scale of 1:50,000. So 1:250,000, another one is at 1:50,000. You can see the difference between them. So a lot of generalization and all these concept, aggregation, amalgamation, exaggeration, everything will be at there. Okay, so this is about the generalization. One of the very important thing in the generalization is the selection. Okay, although it was not listed over there, but the selection is very important. Without selection, or instead of saying selection, it is basically omission. That when we are going to change the scale, several things are going to be omitted. Okay, like right now on the screen, you can find there are several trees on the screen. Isn't it? The small green color point are nothing but the trees over here. So large number of trees are shown at 1:50,000 scale map. But when we go to the next scale, okay, smaller scale, the number of trees in the same area are reduced. Because it is not possible to show all the things when there is a scale change. Omission is one of the most used thing when we are going for the generalization. And you know, it is a very big challenge for a cartographer what to put in and what to put out. And both things are equally important. Whatever you are placing inside the map is just as important as what you are removing from the map. Both things should be done with in a very careful manner, because if you are omitting something, it must be, you must be ensured, or as a cartographer, you must be ensured that those things are not as much as necessary as much the things that are included over there. Here, there are some of the examples. Okay, that what are the different sort of generalization that have taken place. Okay, see the figure. First one is the truth. What is the actual real world truth? And later on, you can see the different sort of generalization that have taken place. Okay. So from truth, the first one is the fused. So what we have used the term, instead of fused, we have used another term. What was the name of that term?
Merging, I think. Amalgamation.
Aggregation.
Amalgamation. Amalgamation.
So I got three answers: merging, amalgamation, and aggregation. Anything else? Just check your copy. You must have written it.
Amalgamation.
Yes. So the final answer is amalgamation, not aggregation. Aggregation is when you are converting several points into a polygon. I have given you the example of ruins, historical ruins for that one, that there are several points that are depicting the buildings. So you are replacing that one by a single polygon, or for any built up area, there are different points that are used to denote building, some hut or something like that. So instead of using that thing as it is, when there is a scale change, you will join them together as a built up area. So here there is a amalgamation. Okay. Next, simplification. Basically, it is a smoothing that have been taken place in this one. Okay. Smoothing. If you read different book, there is a little bit change in the terminology. So that's why this type of thing is occurring over here. There is a change in the terminology. This first one is the amalgamation, second one is smoothing. Third one, displacement. It is quite clear that all these polygons are moving away from the road. So this is basically a displacement. Next, fourth one, some of the small polygons are simply removed. So this is the omission. Okay. Last one, you can see the change in the size of the road. There is a width in the road. Okay. So the road is exaggerated over here. So these are the different generalization. These are the examples of different generalization that we have just studied. Okay. Now, from generalization, is it clear to everyone? Generalization?
Yes, ma'am.
Yes, ma'am.
Now I'm moving to the next topic, which is of map projection, a very important topic. Okay. So you people start saying that you are saying everything is important, but no, the initial lectures are, these all are the foundation, the basic things that are related to a subject. So you must know about these things. Map projection is very important. Why? Because when we are doing a mapping task, what we are doing, we have a curved three-dimensional Earth. And what is happening? That three-dimensional curved surface is getting projected on a two-dimensional flat surface. How this conversion will take place, this come under the map projection. So that's why this is one of the common question that when you are using, like during your thesis viva, it is often asked in the initial work that which projection system that you have used. Why this question is asked? Because you are converting the 3D data into a 2D data, whatever type of data, whether you are using map or something else. Basically, you are doing a conversion of 3D Earth on a two-dimensional flat surface. So that's why you are doing a projection. Therefore, you must learn what map projection means. Okay, so I'm reading it out. To represent the parts of the surface of the Earth on a flat paper map or on a computer screen, the curved horizontal reference surface must be mapped onto the two-dimensional mapping plane. Map projections transfer the spherical Earth onto a two-dimensional surface. It can be defined simply as the mathematical transformation of locations in the three-dimensional space of the Earth's surface onto the two-dimensional surface of a map sheet. The process of projection results in distortion of one or more map properties such as shape, size, area, or direction. If we squash an orange on a flat surface, the skin of the orange will split and spread out in all directions, and the original properties of the orange, such as its shape, will change. A similar change of property will occur when we try to project features on Earth's surface onto a flat piece of paper. Some of the properties of the spherical Earth will be lost, and as a result, the areas and shapes of the features as they appear on the paper will be changed, and the distance and directions between individual features can no longer be maintained after the projection. A single projection system can never account for the correct representation of all map properties for all the regions of the world. Therefore, hundreds of projection systems have been defined for accurate representation of a particular map element for a particular region of the world. So basically what is given over here, a very good example is mentioned in the third point. Like how can you visualize the projection thing? I was telling you that when 3D is getting converted into a 2D, there will be a distortion, or this is what the projection is. So try to visualize this thing with the help of an orange, because when we give the example of Earth, the analogy is often drawn with the orange fruit. So just try to think about an orange fruit and think that if you apply a pressure from the top and that orange will get flattened on a table, what will happen? When you are applying pressure from the top on the orange, what will happen? Because of that pressure, the skin of the orange will break, okay? And orange will split in all the directions when you are applying pressure from the top. So the original shape, the size, everything of the orange will get changed. It will get distorted completely. The same thing we are trying to do with the earth. We are trying to flatten the earth. So when we are attempting to do anything like that, what will happen? The distortion will happen. Okay, there are 4 different types of distortion. We will study about it. But whenever we are doing this thing, there will always be a distortion over there. So that's why there is no single map projection that can be used everywhere. There are hundreds of projection systems, and the projection system is selected according to the region. Okay. Now, before going into the detail, just try to think about the map projection again. Another example, there is one example of the orange. Another example is, let's suppose you have a globe. Okay. Now that globe is made of some translucent material. So when a light source is placed inside the globe, the light which is coming from the bulb will go through the places where there is a water, and where there is a land, the light will not get passed. And if you place that globe inside a dark room, what will happen? Whatever is on the wherever there is a land on the globe, that area will come as a dark, and wherever there is a water, the light will come through that one. Okay, so this is another thing how we try to visualize that if we place a paper around that globe and if we put a light source inside a map, so automatically the land will get mapped on that paper. So we will come to that one later on about the developing surfaces. But right now, we will see about the map projection. Okay, so map projection, if we see the properties of the map projection, there are 4 things. Write it down: area, shape, distance, and direction. Write down in the copy. So in map projection, we try to say following 4 properties: area, shape, distance, and direction. Or in other words, we can say when we are doing the projection, 4 things get distorted: shape, area, shape, distance, and direction. Okay. Now see this diagram. Okay. In this diagram, the distortion of the earth is shown. Like when we are doing the map projection at some of the places, there will be the place will get stretched while other places will get compressed. Okay.
Excuse me, ma'am.
Yes.
Ma'am, please be a little bit slow, ma'am. It's going too fast.
Okay. I will repeat the previous part again. Okay. So when we were discussing about the map projection over here, when we talk about the map projection, what we will do, we will convert 3-dimensional curved earth onto a 2-dimensional flat surface. I have given you 2 examples over here. First example is of orange fruit and another example of a globe. In the first example, I have told you that if you have an orange and if you place that orange on a table, and apply the pressure with your palm on that orange and try to flatten down that orange on the table. What will happen? The cover of the orange will break. Whatever is placed inside the orange, the pulp of the orange will get split in all the direction. The shape, the size, everything of the orange fruit will get distorted. When we are trying to project the three-dimensional earth onto a two-dimensional flat surface, something like that will happen. Now, what thing will get changed when we do this thing? There are four things that will affect it. Those four things are, you have already written down in your copy. Those four things are area, shape, distance, and direction. Okay, so these are the four things that get distorted when you try to flatten down the earth on a flat surface. Another example that I have given you is of globe. Suppose globe is made up of some translucent material. In the globe, if you place a light bulb inside that globe, then the light can pass through the water, but it cannot pass through the land. And if you place that globe inside the dark room and try to take the projection of the globe on the walls or on some other surface, you can see how the world is getting projected, how the earth is getting projected on that surface. Next thing is we are continuing with the distortion that we have just seen that four things will get distorted. Before coming to that those four things, first see this diagram. In this diagram, this curved surface is the earth. Okay, this curved surface is the earth and this straight line. Okay, this straight line is the surface, mapped surface on which the projection will be done. This map surface is intersecting the curved earth at two places, I1 and I2. Okay, and there are four different points that are marked on this earth or on the ellipsoid of the earth: A, B, D, and E. Okay. Now, on this straight line, all these 4 points are projected: A, B, D, E. All these small letter words are on map: A, B, D, E. Okay. Now see the difference in the size. See the capital A and capital B and small a and small b. Similarly, capital D and capital E and small d and small e. Now I will go into the detail, but first draw this diagram and then I will discuss. You yourself try to observe the change in the distance which is given in the figure. Like small ab is less than capital AB, isn't it? This curve, the distance between A and B on the curved surface is more as compared to the flat surface. Now see D and E. The distance between D and E on the curved surface is less as compared to the distance between D and E on the mapped surface. So this is what this figure is trying to illustrate, that when we are doing the map projection, there will be unavoidable distortion. At some places, there will be stretching like D and E. At some of the places, there will be a compression like A and B. Okay, now draw this map. There are a few important facts that are demonstrated in this figure. First thing is distortion may take different forms in different portion of the map. Okay. In one portion of the map, features may be compressed and they will show reduced area or relative distances relative to the Earth surface measurement. While if you go to the other portion of the map, the areas and distances may be expanded. So this is what A and B and D and E are showing. Then there are often a few points or lines where distortion are zero and where the length, direction, and some other geometric properties are preserved. What are those points in this map? This I1 and I2, where the intersection is taking place. Later on, we will cover this thing more when we will learn about the conic projection. But there are some points where this distortion is very less. Okay, or we can say that there is a zero distortion at those places. Finally, the distortion near the point or line of intersection where the map surface intersects the imaginary globe, it is usually less. Distortion usually increases with the increased distance from the intersection point or lines. As you move away from the intersection point or line, like D and E. So if you move away from the line, you will find that the distortion will increases. Okay. Now we are considering all the four properties separately. First property was area. Okay. A map projection may be designed to be of equal area so that any area measured on the map is equivalent to the area measured on the Earth. Okay. So this is the only, it will not happen that you can preserve all the four property. If you go for the one property, rest of the three property will get distorted. So first, in the very first example, the area is taken. So if we try to preserve the area, in that case, at most of the places, the area will be equivalent to what it is measured on the Earth. Such type of map projection is called equal area projection or equivalent projection or homolographic projection. Write down this term in your copy. This one is a new term for you. Homolographic projection. What is homolographic projection? Equal area or equivalent projection is called homolographic projection. So when we try to preserve the area, what will happen? You can see the distortion in this particular example. Just wait. Yes. So this example is showing the equivalence projection. Equivalence projection means equal area projection or homolographic projection. Now try to see the circles that are drawn over here. The size, shape of the circle is getting distorted. But yes, the area is getting preserved. At the top, just near to the North America, this one is the Greenland. Okay, so at the top, there is a Greenland. You can see the size of the Greenland is quite small. And the size of the South America, this continent, the South America continent is large. Okay, I am giving you this particular example because later on I will show you on the shape preserving projection. Okay, so right now this one is the area preserving projection. You can see the size of the Greenland quite smaller than the South American continent, which is true, but you can see the distortion in the shape. How you can observe this distortion? You can see these circles over here. These are drawn so that you can clearly understand what is happening. Along the equator, as you move slightly at this particular point, it is very less, but as you move away towards the equator, this is quite large. Okay. Next one is the shape preserving map projection. So what is shape preserving? A map projection can maintain the correct shape of the spatial features on the map. This property is accomplished by making the scale along the meridian and the parallel the same in both direction. As a result, the relative local angles about every point on the map are shown correctly. Shape preserving projection is also known as conformal or orthomorphic projection. Okay, write it down. Basically, you need to make a proper flowchart for this. Okay. Just wait. Yes. Now you can see on the screen, I have made this projection. You will add the branches to this categorization. So map projection, on the basis of distortion, there are 4 things: area preserving, shape preserving, distance preserving, and direction preserving. Area preserving can be equivalent projection or homolographic projection. Okay. Similarly, there is a shape preserving or conformal. Okay. So this is what shape preserving or conformal or orthomorphic. Write it down. Give this classification the name like this: conformal or orthomorphic. So in this example, you can see this one is the conformal map projection, and you can see the circles that are drawn over here. If you see the size of these circles, they are getting changed. As you move away from the equator, the size of the circle is increasing constantly. Okay, but the shape of the circle is perfect. So this type of projection is called the conformal projection. Now see the change. I have shown you the Greenland and South America in that equivalent projection or homolographic projection. Now see the size of Greenland and South America. Can you observe the change? So in conformal projection, the Greenland is appearing larger than the South America, which is not true, isn't it? So this is what happens when we go for the shape. Yes, the shape will get preserved, but the size property will get distorted. Next one is the distance. Yes.
Ma'am, does it mean that all the circles have equal magnitude?
What is the meaning of magnitude?
Means, ma'am, area. All the circles have equal area, but due to projection, it is being shown differently.
Yes. Yes.
Okay, ma'am.
The size is perfect. The shape is so not the size. The shape is perfect, but the area covered by the different circles are different. Okay, what we want, like in the previous one, okay, in the equivalence projection, the area covered by the circles will be equal, although the shape get distorted over here. Okay, but when we go for the conformal projection, in that case, the shape of the circle is okay, but the area covered by them get changed. This is the second one. Now the third one is the distance. The preservation of distance can be achieved only by selecting certain lines along which the scale remain true. The line of true scale include the central meridian of the cylindrical class of projection as well as the standard parallel of the conic class of projection. Distance preserving projection are called true scale or equivalent projection. Write down in your diagram. Okay, in this one. Now see here. Again, distance and shape and size is getting distorted, but in case of equal distance, the distance remains same, the scale will remain same, but this equidistance or same scale projection will not going to save this thing for everywhere. There is a line of standard, there is a standard line, like if we go for the cylindrical projection, after that we will learn about it. If we go to the cylindrical projection or conic projection, there is a line of true scale. Along that one only, this thing will get preserved. So this is what? This is the equal distance projection. The fourth one is the direction projection. If direction measurement made on the map are the same as those on the ground, the projection is called the true direction map projection. Azimuthal projection preserve direction from one or two point to all the other point on the map. Okay. So direction or azimuthal projection. In this one, the direction will remain true. Okay. Now, when we use such type of projection, this property will not hold for each and every place of the earth. At some particular region, it will remain true. So these are the four different map projection on the basis of property, preserving property, area, shape, distance, and the fourth one is the direction. Now we are going to study the map projection on the basis of developing surface. Okay. In this one, I have given you the example that there is a globe, okay, and suppose there is a light bulb inside this globe, and whatever light is coming from this bulb, it will get passed through the water, but it will get blocked from the land. So when you place some developing surface around this globe, everything will get projected on that one. All the continents, all the land region will appear on this developing surface as a dark color. Now, what will be the shape and how that thing will get wrapped around the globe? On the basis of that, there are three types of map projection: cylindrical map projection, conic map projection, and planar map projection. Okay. First, I will write it down in this one. On the basis of developing surface, there are on the basis of developing there will be a cylindrical projection, conic projection, and inner projection. Okay, so these are the three different type of projection on the basis of developing surface. This will tell you how the surface get wrapped around the globe. So let's read about them one by one. This is the example of cylindrical projection when the developing surface is wrapped around the globe in a form of a cylinder. This type of surface will be tangent at which position, it will touch the earth at which place. Although in this figure, it is not touching the earth, but suppose this figure is wrapped in such a way that it will touch the earth. At which place it will touch?
Equator, ma'am.
Yes. So this surface will be tangent at the equatorial region. Now, if we see one by one about the properties of this one, first one is this particular surface is going to give you the projection of the complete earth, isn't it? Because the cylinder is wrapped around the earth and the whole earth will get projected. How much distortion will take place? It is a different thing. But yes, the developing surface will get wrapped around the earth and it will give you the complete projection. Okay. Second thing, since this projection system is tangent at the equatorial place, therefore it will be true at these places. At the equator and the places near to the equator will be mapped quite correctly with very less distortion. Okay. Next thing, just wait for a minute. Now, as we move away from the equator, slowly the distortion will increase. And if you move towards the pole, what will happen? Anyone? If you move away from equator and if you reach the pole, North Pole or South Pole, what will happen with the distortion?
Distortion will increase, ma'am.
No, in this case, the whole area is represented by the like this grid form. Okay, this is the unwrapped surface which is given next to the cylinder. And what will be the length of the latitude in this case? It will be the equator. Okay, and length of all the horizontal line will be same. It means that the length of the equator will same as that of the equator. It means that it will reach up to infinity. The distortion will be very high because the pole is scaled equivalent to the globe. So the view will be very distorted at the pole. So this is about the cylindrical projection. Usually we prefer the cylindrical projection when we need the map, when we need the projection of complete Earth, and especially when the area of interest or our study area lies at the equator or nearby equatorial region. In that case, we prefer for the cylindrical projection. I will read the things one by one. So it has following aspects. All coordinate lines are straight. Parallel crosses meridians always at right angle. Scale is constant along each parallel. So meridians are equally spaced. All parallels have the same length. The same happens to the meridian. So if the meridian is of same length, is there any problem? Will there be any problem? The meridian, all the meridians are of the same length.
Yes, ma'am. The pole and the equator both will be same. That is wrong. I think.
No, there will be no problem because the longitudes, all the longitudes are of same length. What is meridian? Meridian is equivalent. We use the term meridian for the longitude, isn't it? So the length of the longitude is same. Whichever longitude you will take, the length of the longitude is same for the whole Earth. So that's why if the same length of the longitude is given or same length for the meridian is given, there will not be any problem. The problem that you are mentioning will happen with the parallels. What is parallel? It is latitude. Okay. The size of the latitude is different. The latitude of maximum length is equator. The smallest latitude will be at pole. So the first part will create the problem. All parallels have the same length. This is the problem because the length of the latitude is not same. It varies. As we move away from the equator, it decreases. But for the meridians, that is longitude, all the longitudes are of same length. Okay, so it will not have problem for the longitude. So on the basis of these aspects, a conclusion is made. First, whole world maps are always rectangular. Second, scale is identical in any pair of parallels equally far from the equator. Scale differs considerably among parallels reaching infinity at poles, which have zero length on the Earth but are as long as equator on a cylindrical map. The graticule consisting of equally spaced meridian but unequally spaced parallel. As the parallel get closer to the poles, the spacing between each become wider. With this increase in width, there is an increase in distortion. Therefore, the distortion increases as the projection moves toward the poles. This projection also safeguards the integrity of features at the central parallel and the regions in proximity. Mercator projection is a good example of cylindrical projection. So this is about the cylindrical projection. The next projection is the conic projection. Okay. Try to draw the conic projection by yourself. And first, the conic projection, it will appear like this. There will be a globe and the developing surface will be wrapped around the globe like this way. Now try to draw a figure. When you unwrap this figure, okay, when you unwrap this cone, how the latitude and longitude will appear. Try to draw this thing in your copy. I hope everyone is getting the question. You have a cone. आपके पास एक cone है जो सामने स्क्रीन पर दिया हुआ है. इस cone को अगर आप एक जगह से कट करके अनरैप करेंगे, यही तो काम हो रहा है. सिलेंडर में भी यही काम हुआ कि सिलेंडर को कट करके अनरैप हुआ. So that latitude longitude will appear on that unwrapped surface. उसी तरीके से कोन में भी बोल रहे हैं. कोन में भी आप एक जगह से इसको कट करोगे तब जाकर के ये अनरैप होगा. जब आप अनरैप करोगे तो लैटिट्यूड लॉन्गिट्यूड कैसा दिखेगा उस पर, उसको ड्रॉ
पाई जैसा बन जाएगा.
कैसा बन जाएगा?
पाई जैसा, मतलब
पाई
quarter of a circle इस टाइप से.
Okay.
I'm containing the concentric circles and straight lines inside that is coinciding with the diameter.
Concentric circles.
And inside that
how
lines.
the circle will get formed?
What, ma'am?
How the circle will get formed? You are cutting the cone.
When we are cutting or we are covering the earth by cone.
Yeah, certainly we are covering the earth by a cone and then you have to unwrap that cone. Only then you can get the projection, isn't it?
Ma'am, latitudes will be the same as it is appearing in the globe, and the longitudes will be straight lines originating from a particular center, means the apex of the cone.
Okay. This one is
like
the
this,
final answer. That the latitude will appear like a concentric arcs, not by a complete circle, because I was telling you that we are going to cut the cone. So the latitude will appear like a concentric circular arcs or concentric arcs, while the longitude will appear by the inclined straight line. As you can see that the longitude are appearing like the inclined lines. Okay, so this is how the unwrapping will take place of the cone, and then you will get the complete Earth map. Now let's see the properties of conic projection. The conic projection is a fan shape characterized by an upside down cone over the sphere. No problem. the meridians are represented by the system of equally inclined concurrent straight lines, and parallels are represented by two concentric circles, or simply by the concentric circular arcs. Okay. Next, the angle between two meridian on the projection is less than their true differences in longitude on the sphere. Conic classifications are at an exact scale along a particular parallel or standard parallel. Okay. What they are trying to say, I will show you on the diagram. You know, if you see this cone, it is tangent at a specific point of the earth. Okay, it will touch the earth or it will touch the globe at a particular point. Or if this cone is intersecting, then in that case, there will be 2 points at which this cone will touch the globe. Okay, these point, the parallel or the latitude which is going at this particular tangent point is called the standard parallel. Is it clear? आप जब कोन को ग्लोब के ऊपर रखोगे तो वो किसी एक पॉइंट पर ग्लोब को टच करेगा. उस पर्टिकुलर पॉइंट से एक पैरेलल जो भी पास होगी उसको स्टैंडर्ड पैरेलल कहा जाएगा. इसी का एक वेरिएशन दूसरा जो बताया कि ये कोन ग्लोब को टच ना करके सपोज इंटरसेक्ट कर रहा है, टेंजेंट ना होकर के सीकेंट है, उस केस में क्या होगा, वो 2 पॉइंट्स पर ग्लोब को कट करेगा, टच करते हुए वहीं से 2 पॉइंट से निकलेगा, तो उस केस में 2 पॉइंट्स पर वो स्टैंडर्ड पैरेलल्स आएंगी. स्टैंडर्ड पैरेलल का इंपॉर्टेंस क्या है, यहाँ पढ़िए. Conic classification are at an exact scale along a particular parallel or a standard parallel. Okay? It means that the scale along that parallel will be exact. So what we used to do, instead of taking conic projection of any place, whatever is our area of interest, we try to get it tangent at that particular place. Why? Because the standard parallel that will pass through that point will be at exact scale. And if we move away from that standard parallel, that distortion will get increased. Okay, so this is what the conic projection is, and this is what the importance of conic projection is, because it will not give you the correct scale at the equator. In case of cylindrical projection, if you go around at the equator, that distortion will be least in case of cylindrical projection. But as you move away from the equator, the standard will increase in that case. But in case of conic projection, the place of least distortion or the place of exact scale is the parallel, which is at which the cone is tangent to the globe. Okay. So at any point other than pole and equator, the line of standard parallel can be taken. The third one is planar projection. The planar projection type is an azimuthal orientation of a projected surface, which means that it pertains to the angle of an object around the horizon that is measured from north to east. Planar projection are true only at their central point. The planar graticule represents meridian as a straight line that incline towards each other at their true longitudinal differences. Parallels are represented by a system of concentric circles with their common center at the point of converging meridian or pole. The distortions in the planar type tend to be most prevalent along the edges of the projected plane surface. Okay. So let's see the diagram and understand what is told over here. You know how the planar projection appear. In this one, the developing surface will be tangent to the globe at any place. Okay, like in this example. Okay. Now, first try to draw the latitude longitude again for this one. How the latitude longitude will appear on this planar surface.
Longitude will be radial lines and latitude will be concentric circle.
Yes, correct. So the latitude will be the concentric circles, and the longitude will be the radial lines going outward. This is how the output will appear, or how the projection will take place. Okay. This type of projection is usually used for the navigation purposes. If you see some of the movie and if you see there in the ships and in the planes, you will see this type of diagram over there. Okay, so they use the azimuthal projection, and they are used at a particular path and especially for the direction purposes. Okay, so this is called the planar projection. And in this, only a part of the Earth's surface will be visible. Half of the globe or even lesser of that will be visible. Distortion will be least at the center point where it is tangent to the globe. But as we move away from the center point, the distortion will increase. Okay.
Hello, ma'am, for in sphere, the distance between longitude will be equal. In this, distance will increase from center to.
Yes, it is correct. Because for the longitude, if you see the diagram of the longitude, that the distance between the longitude is not same. At the polar region, it converges, and as we go towards the equator, it will be maximum. Okay, so definitely there will be a gapping. There will be change in the gap between the longitudes. In case of means in actual world, in true also the longitude, the gap between the longitude is not same. But in case of latitude, the gap between the latitude is same. But in case of longitude, it is not same. That's why the latitude is called parallel also. Okay. So this is what the azimuthal projection is, and the surface will be tangent at a particular point where the study is required. Next classification of the map projection is on the basis of aspect. We will cover this thing in our next lecture. Okay, so I will upload this lecture on the MS Teams, and there are few students who have recently joined this team. This is my suggestion that the recording is available. Before coming to the next lecture, just download all those recordings and learn about the GIS that is already been taught, because it will be difficult for you to catch everything because a small portion is already covered. The lecture is already uploaded on the MS Team. The slides are there, book is there, and recordings are also available. If you have any problem in downloading the recording, you can tell me. I will send it separately. Okay, I will upload it again, although there will be no problem. It is there in the recording folder. So that's it from my side for today. Thank you so much. Any question from your side?